Welcome to the Explainer. So, if you spend literally any time diagnosing modern laptop motherboards, you already know the feeling. You're staring at a completely dead board, right? Maybe the fans spin up for a second, maybe a single light blinks at you, but the screen? Just black. Where do you even begin with that? Well, today we're going to completely demystify this whole process for a super specific, really popular architecture, the Lenovo NMB911. You'll find it in the E490 and E5090 laptops. We're going to break down this incredible tool called the ENIT DDR4 debug card, and I'll show you exactly how to read its secrets to pinpoint hardware faults with absolute laser precision.
Okay, let's dive into this. What we're looking at here is Harshad Patel's schematic mapping. And guys, this is essentially the ultimate diagnostic treasure map for hardware techs. It takes all the overwhelming, chaotic complexity of a motherboard schematic and distills it down into exactly what you need to know when you pop your ENI debug card into that memory slot. We're going to unpack every single section of this document today so you can really use it to its absolute full potential.
So here's our game plan for this explainer. First, we'll meet the ENIT debug card. Second, decoding the power and signal lights. Third, we'll track the real signal flow. Fourth, and this is absolutely crucial, translating those readings into actual faults. And finally, test points and some final notes.
All right, jumping straight into section 1, meet the ENIT debug card. Let's figure out what this tool actually is and, where it goes.
The real beauty of the ENIT DDR4 debug card is honestly just how simple it is to use. You just snap it directly into either the Channel A or Channel B DDR4 SODIMM slot on your NMB911 board. Just think of it as your direct, hardwired line right into the brain of the computer. See, because the memory controller is built straight into modern CPUs, monitoring the DDR4 slot means you're basically eavesdropping on the CPU's internal operations and all its attempts to talk to the rest of the system.
But the card alone isn't going to cut it. You absolutely need your motherboard schematic alongside it. The mapping document helpfully points out the exact pages you need to have open. You're going to want page 2 for your block diagram, page 3 for the power system, page 5 for the DDI or EDP display interface, and crucially, pages 6 and 7. Those last two are your main battleground, okay? They hold all the deep, nitty-gritty details for DDR4 Channel A and Channel B. Okay, moving right along to section 2, decoding power and signals. Now it's time to actually learn the language of this card. Now, what's really interesting about this slide is how the map breaks down the power foundation. Listen, before we ever care about data, we absolutely have to care about power. If your 1.2 volt LED is off, you're missing your DDR4 main power. That's the plus 1.2 VDDR VDQ signal. Stop right there. Literally nothing else matters until you fix that. You've also got your 3.3 volt light for slot logic power, VREF for reference voltage, VTT for your termination voltage, and VPP, which is your program voltage. Verifying these lights first guarantees your memory slot actually has the electrical muscle it needs to function.
So once you're absolutely sure the power is solid, we look at the control and clock signals. The CLK LED tells you if the DDR clock is pulsing straight from the CPU. And the reset LED, that one is massive. The little hashtag there means it's an active low signal. Basically, if the system is held in reset, the signal reads low. If it's high, it means the reset has successfully been released. Then we've got CMD for command bus activity, things like row and column address strobes, and ADDR, which watches address bus activity. Basically, these lights tell you if the CPU is actually trying to start a conversation with the memory.
All right, diving into section 3, tracking real signal flow. We know what the lights mean now, but how does the signal actually travel to the card in the first place? Let's trace it.
And this brilliantly illustrates the step-by-step chronological journey of a system booting up, straight from the schematic itself. It all starts over at the adapter, generating your 3-volt and 5-volt always-on power lines. That power then wakes up the embedded controller, the EC. Specifically, that's the ITE8227E chip over on page 2. The EC then fires off crucial signals like the EC on and SLP lines to wake up our Whiskey Lake U CPU. The CPU wakes up, its internal DDR controller fires up, and finally those signals shoot all the way down to the SODIMM slot where our ENIT card is just waiting to catch them. If you're missing a signal on your debug card, the break in the chain happens somewhere along this exact pathway. It's like tracking a water leak, honestly.
Which brings us to section 4, translating readings to faults. Honestly, this is where you earn your money as a tech.
Let's look at our first real-world scenario. You plug the card in. Your clock light is pulsing happily. The reset light is high, meaning the system isn't stuck in some fundamental reset state. But your CMD, your command activity light, is completely dark. So the CPU is awake, but it's totally giving you the silent treatment. So what does this all mean?
Well, it means the CPU is completely failing to initialize the DDR memory. The hardware is sitting there ready, but the digital handshake just isn't happening. Your mapping guide gives you 3 immediate targets here. First, check the BIOS. A corrupted BIOS will absolutely cause this, for sure. Second, check your VCSA. That's the system agent voltage. And third, sadly, you might just be looking at a dead or failing CPU. But the point is, you instantly know exactly where to point your multimeter.
Okay, let's try scenario 2. You've got clock, you've got the reset released, and now your command light is actually flashing. The CPU is actively issuing commands. But your data LEDs, the DQ lines mapping data bits 0 to 63, are totally dead. So commands are going out, but absolutely no data is flowing back and forth. What's going on here?
Let's move to and see how this builds. This specific combination firmly points to a memory training failure. The system is trying its hardest to synchronize with the RAM, and it's just failing. Your next steps are super clearly defined on the map. You need to painstakingly check the VREF reference lines, the VTT termination lines, and the physical integrity of the DQ data lines themselves. You're out there hunting for a broken trace, a short, or a missing microvoltage. But hey, what if every single light is dancing perfectly? You have power, clock, command, address, and data activity all looking great, but the laptop screen is still completely pitch black. Stop looking at the RAM. Actually, scratch that. Stop looking at the memory subsystem entirely. The eNAC card just saved you literally hours of wasted time. Your DDR is perfectly fine. The fault lies further down the line. Maybe it's a corrupted BIOS, maybe it's the EDP display interface, or just another section of the board completely. Okay, moving to our last part, Section 5, Test Points and Final Notes. Let's wrap this up with some critical checks and a few rules of the road.
Check out this fantastic pro tip straight from the source document. The NM-B911 motherboard actually shares its core platform with the NM-A911, which also uses that Whiskey Lake U processor. This means all those signal names we just learned, they are completely identical across both boards. There's really only some minor routing differences. So by mastering this mapping guide, you've essentially mastered the memory diagnostics for 2 entirely different motherboard series at once. How cool's that? And remember, when you actually need to physically probe these connections, grab that schematic and head straight to pages 6 and 7.
So the crucial point is this massive golden rule that comes straight from the guide's notes. init card shows real-time activity, not correctness. I really want you to let that sink in for a second. A flashing light tells you a signal is physically present and pulsing. It does not tell you if the actual data inside that signal is corrupted, and it doesn't tell you if the voltage amplitude is perfectly within spec. The card is your guide, guys, not the final judge.
Which leaves us with one final kind of provocative thought. This mapping guide, it gets you exactly to the right neighborhood. It tells you if the problem is a power drop, a missing clock, or a failure in memory training. But to find the exact house on that street, you still need your traditional tools. The eNIT card points the finger, but your multimeter and your oscilloscope are what actually solve the crime. So the map to the fault is right here in front of you. But will you remember to take that final step and verify those signals with your oscilloscope?